Okay, I would like to answer a few questions raised by some students. First of all, let's come back to this equation for the trajectory of central force motion. Now, as I pointed out last time, if you are given a set of data and you know you can somehow determine the function of the trajectory, then substituting the trajectory or the r as a function of theta into this equation, we can determine the central force generating this kind of a central force motion, all right, or this particular type of trajectory. Now, on the other hand, if we know the force, then by solving this equation, we should be able to determine the trajectory as well. Am I right? So let's take a closer look. If we have a central inverse square law, then the right hand side here will vanish, will become a constant. Right hand side of equation 31 will become a constant. Okay, right hand side will become a constant. Equation 30, same. This is a constant. Then we have an equation very familiar to us, especially in equation 30. If this is constant, then we have a driven harmonic oscillator, okay? And the force is a constant force. So what is the solution? The homogeneous solution will be cosine and sine, right? Cosine t and also sine t. U homogeneous solution is a linear combination of cosine t and sine t. How about the particular solution? Just a constant, right? Because 1 over u square cancel this inverse square law. So the constant particular solution will be minus mu divided by L square. That is the particular solution. Okay? Now combine them, you have the general solution. And then you have to play with the details in order to fix the constants. Okay? All right? Now, if we have, instead of inverse square law, if we have a potential proportional to R square, what will happen? It's an linear force, right? Then one over u cubed, 1 over u, all right? Now, if we multiply both sides by u, then you have, what do you have? Or you just keep it there. So this is 1 over u, and you have our u here, okay? Do you know how to solve this? Can you follow me? If the potential energy is is a harmonic oscillator, okay, radial harmonic oscillator, so it's proportional to R squared, then the force will be the restoring force, linear in R. So the right hand side will be 1 over u. Am I right? How? We know that no matter which one we use, equation 30 or equation 31, it looks very ugly. So that's why we don't pay too much attention to this. You have to do some suitable substitutions in order to solve it. Because by just looking at the equations, this second order differential equation is not linear. Okay. Now, how about the u proportional to 1 over r squared? Inversely proportional r squared. Okay. For the potential. Proportional to u cubed. You mean this, the right hand side will be proportional to u. Can we know how to solve it? Yes. So you should know that sometimes for certain potential or for certain force, this equation is useful, but for the others, it is not. Okay. Okay, another question is about Runge-Kutta, no, Runge-Lenz vector. This is about this. Okay. Now, the most important point about this Runge-Lenz vector is that if the u, or if the force is not inverse square law, does not obey the inverse square law, then this part won't be equal to a constant. All right. So this constant motion is very specific to inverse square law central force. It won't work for all the others. Say, for example, if you have a Yukawa potential, that means 1 over r time an exponential decaying factor. Even though the decaying factor is extremely slow, okay, almost like 1 over r potential, Coulomb potential. But as long as we have that factor, the Runge-Lenz vector won't be a constant motion. Okay, so this is a very specific for the Runge-Lenz vector. Here we show that it should be a constant motion. Then it also implies that the Poisson brackets of this Runge-Lenz vector with the Hamiltonian must vanish. Am I correct? Because if we take the time derivative of this Runge-Lenz vector, it is equal to 0. Then, according to Hamilton's equation, the Poisson bracket between A vector and the Hamiltonian function must vanish, right? Yes. No, you just write down P vector square over 2m plus the potential function. The potential function depends on R only, right? And this vector is defined as this, P cross L in vector form minus mu k over R times R vector. No, it takes Cartesian coordinates. They go and take spherical coordinates. They go and take cylindrical coordinates. It won't matter. Definition. For example, bracket of A and H, right? Cái gì biết là nhưng mà cái con rất là ngắn lắm.得唔得？所以咧，我哋唔一定要係根據呢個去 prove 嘅，得唔得？你可以 check this program bracket。嗱，如果你有興趣咧，你哋應該會諗下啦。嗱，呢個 A 咧好得意喎，佢同個 L 又有關喎，係咪 ？L 有關喎，咁個 L 咧又係 constant motion 喎。L 同 H 嘅 Poisson bracket 咧係會等於幾多？0，冇錯啦。嗱，記唔記得本身 angular momentum 有一 set of Poisson brackets specific to angular momentum component 有冇印象啊？我哋好早做過㗎啦，就係 L、X、L、Y、L、Z 佢哋相互嘅 Poisson brackets。咁咧，同埋個 Poisson bracket of each component with L square vector square 有冇印象？嗱，咁既然呢個 A 又係一個 vector 咯，有冇同樣嘅嘢嘅咧？得唔得？會唔會有同樣嘅嘢嘅咧？仲有就係 L 同埋呢個 A 嘅 Poisson bracket 會係點嘅咧？嗱，如果你有啲同學咧，係遲啲會讀一啲深少少嘅數學嘅話咧，你就會留意到咧個 Poisson brackets 咧包含咗呢 L 啊同埋 A 呢啲 constant motion 咧係會擴大嘅。如果淨係睇 angular momentum 咧，你知道 Lx 同 Ly、Ly 同 Lz。咁如果 L square 咧，咁樣係嘛？咁而家問下個 A 係咪有嘅咧？咁啊 A 咧似乎又好似有類似嘅嘢嘅喎，但係咧 A 同 L 咧互相嘅 Poisson bracket 會唔會係 form 一 closed set 嘅 relation 咧？OK？得唔得？咁咧呢六隻嘢咧，即係六個 component 咧 ，L 一、L 二、L 三、A 一、A 二、A 三，咁佢哋本身咧就會幫住一個咩？專係個 inverse square law 嘅 power 一個嘅 constant motion set， 而係用一個 technical term 咧，所謂 associated 嘅 V-symmetry， 即係with this system，OK？ 咁佢有個 group 嘅，咁但係當你遲啲你有興趣讀啲 V group 啊，咁你會學多啲呢啲嘢啦。咁調翻轉頭會問下就係話，我可唔可以即係我唔識 physics 啊，唔識 physics 佢嘅情況，其實我哋都可以由個數學嗰度推翻啲 result 出嚟嘅，即係調翻轉，OK？ 咁呢個咧就係其實對於理論物理方面係經常會用嘅。好多時候去到一啲地方，你係 any something new， 你又冇乜實驗嘅，咁你就會咧appeal to symmetry。會唔會我哋 擴大呢個 symmetry 擴大個 symmetry 嘅嗰個 system， 會有啲失誤出現咧，係可以假嘅嘛，唔一定啱嘅嘛。咁呢個係一個嘗試嚟嘅。OK， 咁記住咯喎，嗰個無論係任何一個 constant motion， 到底係 vector 啦、scalar 啦，你如果佢係 constant motion 咧，佢嘅 Poisson bracket 同你係當然咧都係 vanish。所以你一係咧將啲 time derivative 嗰個 constant motion 係等於零 ，or Poisson bracket between 個 constant motion 同 h 係等於零。不如玩一玩啦！嗱，你又知道個 A 啦，係咪跟住係 commute 嘅咧？即係咪個 Poisson bracket 等於零嘅咧？係咪通常好簡單嘅？ P vector square over 2m 加嗰個potential energy 就係 1 over r 係嘛 ？K over 1 over r 啦 ，K over r 啦 ，minus K over r。如果你做嘅時候，你又唔使 prove 係成支 vector 喎，點解啊？你搞掂咗一個 component， 其他嗰啲 component work 噶啦嘛，係咪？咁你 take one component， 譬如 AI 咁樣，其中一個 component。點解你唔用翻你哋經常用嘅？有個 AI 係咪 ？AI 係啲乜嘢啊？IAK、EK、LK， 記唔記得 ？minus K over R XJ XR。 唔好以為好複雜啊。Now keep in mind that when you play with the Poisson brackets, there are two different things you have to keep in mind. Remember the arithmetics, okay, and also the definitions of Poisson brackets. Sometimes it's better to use the definition directly. Sometimes it's good to play with the arithmetics based upon some fundamental Poisson brackets. So if you can find the Poisson bracket between the Runge-Lenz vector and the Hamiltonian equal to 0, then it's all set. It is a constant motion. 嗱，大家諗下第一個 term of A，the first term of A。如果你 evaluate 個 Poisson bracket between the first term and H， 你同有個 L， 基本上好似 constant 咁啦。跟住個 kinetic energy term 同呢個 B 又係 constant 啦，係咪等於零啦？所以剩翻落嚟嘅係乜嘢啊？就個 potential energy 嘅啫，得唔得？對於呢個嚟講，得唔得？如果你要 evaluate 個 Poisson bracket between A、I and H， 我哋知道你 play with 個 arithmetic， 你都要揼落去啦。咁因為對於 LH 嚟講，呢個 LH 係好似 constant 咁噶嘛，係咪？你唔需要再做到咧，等於零噶嘛，得唔得？記唔記得個 arithmetic 啊？如果唔係你做親，嗱記住你嗰啲 tools 教晒你㗎啦，但係你要靈活運用，得唔得？又要有時要用 arithmetic， 有時要用 definitions。咁呢幾時用到咧？就係用咗佢，係咪？個 LK 同佢係 vanishing 㗎嘛，個真嘅，所以只有剩翻呢個嘅啫，個 PJ 嘅啫。咁 PJ 咧同個 kinetic energy term 咧，又係零嘅喎，個真嘅，係嘛？咁所以剩翻嚟啦，就 potential energy 嘅啫，得唔得啊？咁呢個啱啦，同個 potential energy 啱啦，好明顯係零啦。所以呢個咧同個 kinetic energy term 有關嘅啦，係咪？咁就好快脆完。如果你減粗啲啊，用個 definition 咧，咁對住 professor 講就話呢啲唔係人做嘅，因為你係咁壓係咁壓嘅話，你實會一大劈嘢㗎啦。OK？ E vector square over 2m 2u a e I square minus g over r。你有需要唔講，冇需要唔講，係咪？係嘛？嗱，你諗下啦，正話都講呢個 term 同呢個個 term 嘅係零嚟㗎嘛，大家都係分出嚟包，係咪？你包做乜嘢咧？但係如果你入翻去覺得呢條路咧，就好 tempting 㗎就，即係連 D 去啦，D 完一大嚿之後咧，你就發覺到哎呀等於零呀咁樣。如果唔好彩咧，計錯數咧，咁就玩完啦，得唔得？因為有個同學問我話，你咁樣 D 法 D 完之後，你收到個 constant 就等於零，咁就 constant motion 啦。咁樣可唔可以用Poisson bracket嘅咧？個 answer 係得嘅，一樣嘅啫。無論係 DA vector DT 同係 find the Poisson bracket between A 同埋係個 H 係一樣嘅啫。得唔得？而家可唔可以快啲啊？而家做得？我想問咧，如果你有個 iPad，點樣可以喺個 share screen 度做到出嚟啊？譬如你哋而家做咁樣，點可以寫到上去？即係啦，係啦。 即係你譬如話，我而家譬如話咁講啦，就係、我而家想借你家聽，用手寫落去啦，係咪啊？係咪啊？但係微博要鏟咗呢個去㗎嘛，睇唔到㗎嘛，明唔明啊？唔得嘅。OK，啊，OK。嗱，首先我哋玩個咧就係 AI X 嘅過山車 ，OK？咁咧就係 Epsilon I J K E J L K 同過山車同人工人嘅過山車嘅。第二個就係 mu K X I over R 同 X 嘅過山車嘅，得唔得？多到邊？mu K X I over R 咯，係嘛？啱嘛？OK，咁啊，即刻就等於呢個啦。等於乜嘢啊？就係 Epsilon I J K L K E J H minus U K X I over，因為咧個 X 裏邊咧有 potential energy term，係係啊，你即係話自己嘅。好，我重寫翻先。得唔得啊？哎呀，真係唔掂，唔搞你嗰個，俾我搞翻你。我諗啊，寫到咁上下啦，可能你幫我寫會簡單啲，得唔得？ 係啦 ，Poisson bracket between Pj 同埋 H。係 H 都得，你寫 H，OK。嗱，下一步咯喎，將第一個 H 嗰個 H 喺 Poisson bracket，第一個 Poisson bracket 個 H replaced by potential，點解啊？因為 kinetic energy term 係 Pi square 嚟㗎嘛，咁一定係等於零啦，係咪？得唔得？所以第一個 H 喺第一個 Poisson bracket 嗰度個 H 咧 replaced by 個 potential energy，第二個 H 咯喎 replaced by kinetic energy only。嗱，睇清楚咯喎，XIR 係啦，跟住就 kinetic energy term only 2 μ 搞掂。嗱，如果去到呢步咧就易好多啦，係咪？無論你係想直接 D 佢又好，直接係再 play with 嗰個 arithmetic 就好，隨便你啦。你想點都得啦呢度，得唔得？仲有喎，呢兩組嘅嘢其實有啲似嘅喎，你睇清楚就知㗎啦。點解咧？嗰個 angular momentum 係點嚟㗎？又係 epsilon KLM XL PM 係嘛？有冇印象啊？angular momentum LK 等於 epsilon KLM XL PM 得唔得？我寫俾你睇。LK 等於 epsilon KLM XL PM。咁你已經可以睇到個兩個 term 嘅已經好多地方係好似㗎啦，已經得唔得？嗱，第二個 term 就係呢個 potential function 加個 sin 呢個 potential energy term。第一個 term 呢個有 P 跟住 potential energy，但係個 L 裏邊咧其實有個 P 嘅，亦都有個 H 嘅，得唔得？咁呢度做個分Poisson bracket 咧，你拆開兩個 term 嘅，因為突然間個周邊係 Pi 係嘛，有兩個 OK。OK，咁我哋用由即係讓你自己去玩啊！但其實最主要就係個 L 個 commutation，L 個同 H 個 Poisson bracket 等於零，呢個最重要嘅。如果你唔留意呢樣嘢咧，你就好慘㗎啦。同埋個 kinetic energy 同個A 只係個 potential energy 有嘅啫，得唔得？第一個 term，第二個 term 就係只係 kinetic energy 有嘅啫，得唔得 ？OK，好啦，咁其他嗰啲你慢慢一定砌到出嚟㗎啦。 Oh.嗱，咁跟住又記住一個 fundamental 嘅 relation 咯，就係 xi 同埋 pj 係等於幾多啊 ？Kronecker delta function ij 係咪啊？無謂再 D 啦，記實呢個 ，OK？大家都好好好熱烈想繼續做落去。咁我 take 5 minutes break 俾你玩埋多陣啦。5 minutes break。OK，this is our final topic. It's about scattering orbits, scattering orbits. They are orbits corresponding to a total energy greater than 0 for the inverse square law, such that R vector is not bounded. They are also the only type of solutions for potentials modeling the two-body repulsion interactions. Because the 1 over R, if it is repulsive, then they just add up, and the effective potential will be positive for all R. Okay, so typically the interactions vanish for large R, and the particle is asymptotically free. And the vector R will move towards the pericenter with a minimal distance from the center of mass, i.e. the origin. And you can see here, our particle starts from negative infinity, or from infinity, from far away. Share screen. Let me see. Yeah. Okay, it works now, right? Okay, we start with, today we are going to look at the scattering orbits corresponding to positive energy. Typically, the interactions vanish for larger R so that the particle is asymptotically free with a constant velocity when they goes to when they are far away from the potential center or from the origin. So from this diagram, we can see that the particles start from far away from the origin or from the scattering center, move in, all right, and it will come to the closest, come to a point called pericenter, which is at a minimal distance from the center of mass, i.e. the origin. And then it will move away, okay? Now, when it goes to far, when it goes to infinity, the motion becomes almost uniform again with a new constant velocity. Now, for conservative interaction, the total energy is conserved, so the incoming velocity and outcoming velocity should have the same magnitude in order that the kinetic energy is conserved because the potential energy is approaching zero. Okay? And you can see that the trajectory of the particle has changed by an angle. Okay? And this angle, we call it the scattering angle or the diffraction angle. It is the phi prime. From the diagram, we can see that phi prime are related to the maximum theta, the maximum angle, the theta angle. Here you can see that phi prime is equal to pi minus 2 theta max. Okay. How can I get rid of this one? Okay. Hay à, này cô. Đây rồi. I see. Okay. Okay. Yep. Thank you. So from this diagram, you can see that the phi prime and theta max are related according to equation 1. Pi minus 2 theta max gives you the phi prime. Okay. Chỗ thằng xíu xíu, ok. Xong đó. Cũng nhau đó. Thì điểm cái mình tắt cho nó. Comment tâm ta? Ý điểm hơi biết không? tâm ta咁樣。個部出體有冇啲咩遙控器？我唔知喎。睇咩到啊？你而家？得唔得咁樣 ？OK， 好啦。Now the angular momentum is conserved because this is a central force problem, and it is equal to mu r v naught prime sine alpha. You can see it from this from this diagram. there's a typo here. There's a typo here. It should be mu r v naught prime as well. Okay. The final term, the final one. There's a typo. Okay. Sine alpha is the same as sine pi minus alpha. Yes. Right. It's something like the light, just like the light coming in, hit the plane and go out. Think about it. And no matter, and also it is symmetric. The part coming here. It is good. This side. Right. T is normal. It's the shortest distance. It's not really a parabola, hyperbola. Hyperbola. Okay? It's a hyperbola. You come in a different position. So we have a theta. When you go far away, you get an infinity, right? So that is the maximum. So you start from theta max, from very far away, and come near the center, and then go far away from the center. Okay. Now, there is a term called impact parameter. Okay, impact parameter. The B is equal to R sine pi minus R. Okay, we call it impact parameter. Okay, so the angular momentum can be related to the so-called impact parameter. Actually, it is equal to R sine pi minus R alpha. Okay. Now, for positive, for repulsive potential, the phi prime is positive. For attractive potential, the phi prime is negative. So it's curved downward. Now, according to the trajectory, the conic section, d theta dr is equal to this. We have shown this before for the central force potential. Okay, central potential. Now, in order to get the trajectory, we have to integrate this. Okay, so we start from theta equal to 0 from the pericenter to far away from the origin. Since the distance r increases monotonically, when it goes far away, it starts from the pericenter and then go to infinity, right? So we can choose the positive sign, assuming L greater than 0, and obtain the expression for theta max. Okay, you can look at here. You start from this point, P, and go all the way out. Go all the way out. Then you hit a point. R goes to very, very far away, infinity, and it is free. And the angle becomes theta max. In other words, it hit the asymptote of the hyperbola. Now, to perform the integration, we still need to know the R mean, the shortest distance at which the radial velocity vanishes. How do we find the R mean? it is equal to E minus U min minus L over 2 mu R square min equal to 0. Okay, the radial velocity equal to 0. Since B is defined by this and E is defined by this, the initial total energy, all right? So we can plug it in and do the integration, and we are all set. But as you know, unless it is the inverse square potential, it is almost hopeless for general potential. Okay. Now we know about the impact factor, impact parameter, which is related to the angular momentum. Another term that is very important for scattering is the scattering cross section. Okay, sigma. What is scattering cross section? If the scattering is head-on collision only, very simple. If we have a sphere, then the scattering cross section will be equal to the area the particle sees. All right. However, the scattering interaction is a long-range interaction. So this sigma is no longer the same as the size of the scatterer. Okay. How do we determine the scattering cross section? Let's look at this diagram. If we send in a beam, a beam of particles passing through this small surface, d sigma, in the screen plane S, and we come close enough to the scattering center, it will be deflected. Okay, and finally hit this solid angle, elementary solid angle. We put a detector over there. All right. And we are interested in this ratio, d sigma, d omega. And this is the so-called differential cross-section. What does it mean? We send in a beam through this d sigma. We want to find how much it will come to this solid angle, or measured by this solid angle. Okay, so it's sort of like telling you the distribution or the probability of hitting this d omega. What is d sigma? The shortest distance is the impact parameter. So d sigma is equal to 2b dB. Okay, it's a ring, a circular annulus, because we have a azimuthal symmetry about the z-axis. So d sigma is equal to 2b dB. How about the solid angle, elementary solid angle? Once we know the phi prime, we know the solid angle. It is equal to 2 pi sine phi prime d phi prime. How do we get this 2 pi here? Azimuthal symmetry. Okay. Okay. So d sigma is 2b dB. D omega is 2 pi sine phi prime d phi prime. It's a ring, annulus. Yes, yes, you're correct. Here I have a pi here. Okay, a typo. Okay. So the d sigma d omega is equal to 2 pi b db divided by 2 pi sine phi prime d phi prime. Okay. Now the magnitude of the derivative db d phi prime is taken because for scattering problems with a repulsive potential, the derivative is negative. However, the differential cross-section is only meaningful for positive values because it basically measures the probability of hitting this elementary solid angle. Okay, it tells you the probability, how much will come from, how much of the beam passing through d sigma will hit the elementary solid angle. Okay, so it's a ratio. That's why we take the absolute value here. Now, for the inverse square law problem, Keplerian problem, we know about the hyperbolic trajectory. It is equal to this, r theta equal to alpha over 1 plus epsilon cosine theta. Alpha is equal to L squared over mu k. This is the eccentricity. The range of theta is limited with cosine theta max. And that is equal to minus 1 over epsilon because it is a hyperbola. Now, in accordance to equation 1, let's go back to equation 1. Okay, equation 1 here, phi prime equal to pi minus 2 theta max. We can rewrite equation 14 as this in terms of phi prime. Okay, so the eccentricity is related to sine phi prime over 2. And this sine prime over 2, this sine phi prime over 2 can also express in terms of the total energy and also the total angular momentum. Okay, because epsilon is equal to square root of this. Okay, 1 over of this. Now, if we define another parameter called P naught, we can simplify this expression as B squared over B naught squared plus 1. Okay? Now, this is the sine phi prime over 2. We can make it even simpler. We look at the tangent of phi prime over 2. That is equal to minus B naught over B. That's trigonometry. Okay? Trigonometric identities. Now, if we plot this phi prime as a function of this B naught over B, we'll see that for repulsive potential, the phi prime start at pi and then decay to 0. Okay? On the other hand, for attractive potential, the phi prime will start at negative pi and decay to 0 as B gets bigger and bigger. Okay, B over B naught. Now, using 11 and equation 16, 11 and equation 16, definition of the differential cross section, and this relation, equation 16, try to show this Rutherford scattering formula. Okay? This is a historically and practically important formula for scattering, for inverse square potential, inverse square law, or Coulomb potential. Now, no matter whether it is gravitational force or electric force, Coulomb potential, you get the same answer. Okay? And if you go to quantum mechanics later, you use wave mechanics to derive the scattering cross sections. And it turns out magically that we get the same formula again. Okay, whether you are talking about quantum scattering problem or classical scattering problem, as long as it is inverse square potential, inverse square law, the classical formula is the same as the quantum formula. Okay, this is a magic. Okay, now you can plug it in and see what happens. All right, I'm not going to further details about scattering. I just want to introduce what differential cross section is. If I want to find the total cross section, what should I do? Sigma. If I want to find the sigma, now as I said before, if we have a head-on collision only, the sigma will be the area of the scatterer, right? But now we have a long-range interaction, integrated. So actually we integrate over the 5 prime, right? We integrate over the 5 prime. That is the scattering angle, okay? Or diffraction. 呢個就係個 probability， 即係話你有一個 unit 啦入嚟，經過呢個 d sigma deflect 咗之後，入可以 reach 到你 detector，which is located with 5 prime。OK， 咁你要揾晒嘅，你係咪要積晒佢啊？你即係你放啲 detector 周圍都有啦，冚晒佢啦。但係實驗唔會啊嘛，所以呢個先係最重要啦 ，differential cross section。OK， 咁當然啦，你要 normalize 翻佢，你就要睇下有幾多入嚟，幾多出去。咁你就 count 啦。如果你真係做實驗嘅時候，你就 count the numbers。OK， 喺唔同嘅 file 你嗰個 number 有幾多，咁你就會個 probability 出現啦。OK， all right, I think I'll stop today here. In the next class, I will try to do some review problems with you. Okay. Any questions? Yeah, go ahead. Which one? Maybe I just stop the share. Okay, so that's it for today. I'll see you on Thursday, and we'll talk about the review problems.